Welcome everyone, and today we'll discuss about power factor. Well, these two words, every electrical and electronic student has heard them, and most of them think they know about it, but they don't. And I don't blame them completely because the way it is generally taught, they are mixed in heavy formulas, right? Heavy mathematical formulas, and also a lot of phase shift diagrams and other textbook jargons, right? So it's very easy and natural for them to get it confused with something else entirely. So in this video we are going to strip all of that away and focus just on the idea, the intuition, and the world around the power factor, right? So let's begin. And to begin with, very first question that comes to my mind is my power factor and efficiency are the same thing or not? Well, this is the most misconception around this topic. So let's clear it with the help of an example circuit. So I have the load here, a bulb, and I have connected it to a DC source in the circuit whose voltage is V and current is I in, right? So now let's say the energy provided by my source gets converted by bulb into light energy, and some of it is getting converted into the heat energy, right? So let's say, for example, the power provided by the source, which is my battery, gives 100 watt, right? So what will be the power input at the load? So in our case it will be 100 watt too, right? So now let's say the conversion factor. So my bulb converts the 100 watt of input energy to light energy, which is 5 watt, and rest of the 95 watt is converted into the heat energy. So what will be my efficiency? The efficiency is defined by desired output power by the input power at the load. So you see, we are isolating the load. The load is our system, and at the load side, what is my input and what is my desired output, right? So in our example, if my desired output power is light, what will be my efficiency? Which is, it will be 5 by 100 or 5%. If my desired output power is heat, so my efficiency will be 95 by 100 or 95%, right? So you can see the efficiency is changing based on the desired output power, but it is talking about the same term, power. Whereas power factor asks a very simple question: is the output energy, all the output energy provided pushes out by the battery, has reached my load or not? Yes, in our case all the 100 watt coming out from the battery is reaching at my load, so my power factor is 1. So in layman terms, if I have to define my power factor, it will be the input power at the load divided by the output power by the source, right? So how much of the output power is reaching my input power at the load, right? So that is my power factor. In DC case it is always 1. Well, if my power factor is always 1, the term would have never been coined itself. So let's see what is happening in the AC world. So all the straight line in the DC comes into a sinusoidal waveform in the AC world. So here is my voltage curve, right? And this is my current curve. So if you notice, both of them reach at their peak at the same time. So right now, if in the previous example I replace my DC source with an AC source, the power factor will still remain 1. Why? First of all, they are in phase. Secondly, because of the resistive element. But the moment I add a reactive element like capacitor or inductor in my circuit, the equation changes completely. Yes? So I'll just redraw my graph where I'll redraw my current curve and voltage curve. So here is my voltage curve on the in the marked in the red, and my current. So now based on the reactive element, my current will either lead the voltage marked in the straight line, or it can lag the voltage marked in the dotted line, right, based on the reactive element that I have taken. So this shift between the voltage and current is nothing but phi, and the cosine of that phi is my power factor, right? Also do notice the change in amplitude of the current in both the curves, in this curve and the previous curve, right? And the reason for so will be discussed in the upcoming section, right now let's focus on why this shift is happening because of the addition of a reactive element. What exactly they do? So whenever we add a reactive element like capacitor or inductor, what they do is they store energy either in magnetic field or electric field provided by the source, right? When the source charges them, they store energy and then they release it back. They release it back to the source, and this oscillation, and it keeps on oscillating, and this oscillating energy is nothing but my reactive power, right? So I'll just read on my original circuit. So here is my bulb, and I have added a capacitive reactive element, and I have a AC source in my circuit, right? So now the AC source charges my reactive element, right, during the one cycle, and during the discharge cycle the reactive element give the energy back to the source. So there is always an oscillation going on, and a part of the energy provided by the source goes to the load, which converts it into light energy and heat energy as well, right? So now my source has to provide not only for the reactive element but also for the load, right? So the source has to accommodate for both, right? So now comes where I have to define three types of power. One is real power, second is my reactive power, and third is my apparent power. The real power is denoted by R, reactive by Q, and apparent by S. Apparent power is nothing but the power provided by the source. Real power is nothing but the power consumed by the load or reaching the load. Reactive power is the energy or the power that is oscillating between the component and the source, right? So in many places you have seen a triangle, right angle triangle, where the base is real power, adjacent is reactive power, and hypotenuse is my apparent power, and there will be a phi angle between S and R. So right now my power factor will be defined as how much of the apparent power is real power, so real power by apparent power, and if you take the triangle, the power factor will be defined as the cosine of the angle between S and R, which is cos phi, right? So in order to let's take an analogy to get a good understanding of power factor further. So I'll take a glass, right, and I'll pour a coke inside the glass, right? So the coke will contain some liquid part, right, and a foam on the top of it, right? So if I take this is my liquid part, the bottom part, and on the top there will be foam, and the glass itself, which is holding both of them, I will consider it as a total, right? So my liquid is my real power. Why? Because it is going to quench your thirst. Foam on the top of it is real but is not doing any real work, but it is present, so it is by reactive power. It is present but is not doing any real work, and the glass itself is my source, which is my apparent power, right? So if my apparent power is 1 liter, let's say my liquid is 0.7 liter and my foam is 0.3 liter, what will be my power factor? Based on the equation above, my power factor will be real power by apparent, which is 0.7. Now if I have another coke bottle from another brand, I pour it into the glass, and I got the liquid part as 0.3 ml, and rest of the part is covered, or on the top of it will be foam, right? So now if I consider in same 1 liter of glass, what will be my power factor? It will be 0.3. So now if your thirst is going to be only quenched by consuming 0.7 liter of liquid, what has to be done to this source? It has to increase in size, yes, to increase my the amount of liquid inside it to reach it to 0.7 liter, correct? So my source has to increase. So whenever my power factor is decreasing, my source has to increase in size to accommodate for the same real power, right? So the real power is nothing but the power consumed by the load. So let's say if in the grid, there will be a grid in the city and it provides power to your home, right? So your home will have many load that will be running, and combining all of it, the power factor is 0.3. So what will happen? Your reactive power is very high. This means your reactive power is very high. If reactive power is very high, means there will be a lot of energy that will be oscillating between source and your home, right? Because it always oscillates and it's not doing any real work, but it is contributing to your I square R losses. Yes. So now, if what will be my apparent source if my real power is 1? So if my power factor, we have 0.3, my real power is 1, what will be my apparent power? So my apparent power will be 1 by 0.3, which is 3.33, right? So my source has to be 3.33 times in order to work for the same real power 1 watt. So now let's say if you have not one house but 3 to 4 houses in your locality, and every house has a power factor of 0.3, what will happen? And it's connected to the same grid also. What will happen? My power, just imagine how big the source will be needed. Because why? Because the source has to accommodate for the Q for all the houses, which is reactive power. The source will be very high. On paper it is possible, but not on the actual practicality. So generally power factor is kept above 0.7 or zero point 0.9, and that is the preferred range, right? So why does it matter to you? So let's say if you are a hobbyist, so if you are working on a PCB and there is a fuse that is, and from the fuse there will be a circuitry that is getting powered on, right? And every time whenever you connect the power source, your fuse is getting blown. So there can be a reason that your power factor is less. If power factor is less, your current will be very high, even though you are working on the same wattage. But since the current is very high, your fuse is getting blown. So you can have a look at your power factor and it can resolve the issue, right? So now let's say in the previous example, instead of our house we have industries, and all the industries are loading my grid, right? So what will happen? The source, it can really load a grid. Instead of, we take an example of a house, so they are contributing to I square R losses, because high reactive element, they will contribute to I square R losses. So in certain countries, what happens is the government regulate how much power factor you can have, and generally it is greater than equal to 0.9, and if it is less than 0.9 you will be fined heavily, right? So that is where the government comes in. Also there will be a question, right, whether we can increase my power factor or not, whether we can reduce, whether we can stop the flow of power that is going to my source and catch it in middle. Well, yes, that is where the idea of power factor correction comes into picture, but that is a topic for some time else. In the next video, maybe you can let me know in the comment section below if you want to know more about power factor correction. So let's see what we studied today. So power factor is not equal to efficiency. We have seen types of power: real power, right? Real power, reactive power, and apparent power. So these are the three types of power that we have seen. Today we have seen the triangle. We have also seen the representation of the same, and we have seen the formula for the power factor. And also we got to know why it is important if you are working on a PCB level, or you are working, or is it a part of your home, or is it a part of your industries. So this is all what we have learned. If you find this useful, please do like the video.